Okay, this is AP Lecture 1.1, Unit 1, first lecture of this series. And today I'm talking about the idea of analytical chemistry, but now working towards not just from grams and percentages as we did in class last week, but now working in terms of molarity, dilution, and eventually a little bit of precipitation analysis. Okay, a little review here. Molarity, okay, if you remember, is big M, and it's equal to moles of solute, the substance being dissolved, over a liter of solution. Okay, now it's important you understand how a molarity works. We usually use a volumetric flask to make a solution. My drawings are horrible. There's a little line here that usually represents the amount we're talking about. In this case, we'll just pretend it's 1 liter. Volumetric flasks are very precise pieces of equipment. In any case, when you make a 1 molar solution, let's say of NaCl, what we're going to do is we're going to take 1 mole of NaCl, and we know that from formula mass, 1 sodium is 23 grams, and 1 chlorine atom, a mole of it, okay, is 35.4. And we'll just use 35 for this example. So we get 58 grams per mole. So we're going to add 58 grams of sodium chloride into the flask. There it is. And then we add the H2O to fill the remaining volume that's left unfilled right to the 1 liter mark. Often I have a lot of students who think that molar solutions are when we take a 1 liter of water and then we add to it, let's say, the 58 grams. Of course, you guys know from Archimedes from last year that 58 grams of the salt would basically take some space of the water and push the water, buoy the water out of there, water displacement, and we have over a liter of solution. So understand, normally we put the salt in first, then we add the water up to the line. Obviously we don't have a liter of water, this is a liter of solution. Very important that you understand those differences. Okay, so that's molarity, and we're using moles, and from grams and moles from the periodic table and formula mass we can go back and forth. But it's a way of looking at a solution and linking the mole concept into a solution. Okay, dilution. Dilution is the idea that we already have, let's say, a 4 molar solution, and we want to dilute it, let's say, into a 2 molar solution. What we would do is we would add water. Okay, or we add some volume of water. There's a couple different ways to do that, but the most famous way is MV equals MV. Now real quickly, the reason why MV equals MV, if you break it down, and this is called dilution formula, because molarity is moles over liter, and volume is, let's pick liter, and then we have moles over liter in this scenario, the new scenario, and then of course we have liter. And if you multiply mole over liter times liter, you can clearly see the moles of the solute on this side are still the moles of the solute. We're not changing how much solute we have, we're just changing the volume it's dissolved in. And that's why we can do that. Now, there's another way to do this method, MV equals MV, okay, and there's a couple of pitfalls later on when we get to acid and bases where this is not the best method, and I'll show you both when we get there. All right. Now, precipitation analysis is going to be a few labs away, but I'm taking this opportunity to plant the seed. Precipitation analysis is the idea that we have, let's say, for instance, we have sodium chloride, aqueous. Oops, little doohickey you'll get rid of there. Doohickey is not a scientific word, so don't fret or treble clef about that. That's NaCl aqueous. So we have that in a beaker. Now we really know what that really means. Now let's say we have an unknown concentration of sodium chloride. Okay, how do we figure out the actual concentration of the sodium chloride? Well, the first thing I do is if I look at sodium chloride, I can see that it breaks apart into Na plus and Cl negative ions in solution. Okay, now these ions in solution are a 1-to-1 ratio. 1-to-1 meaning if I can figure out how many chloride ions are here, I certainly can figure out how many sodiums. If I figure out there's 1 mole of chloride ions, there has to be 1 mole of sodium ions, so forth and so on. So precipitation analysis, to figure out, let's say, how many sodium ions, I know I said sodium chloride, I'm changing the scenario here. Let's say you want to figure out how many sodium ions are in solution. Okay, well, let's pretend the sodium ions came from sodium chloride, but what I would do is, since sodium is always going to be soluble, and there's reasons behind that, I love to talk about that in class, what we're going to do is we're going to add another ion, let's say silver ion, and silver ion is going to precipitate with the chlorine, which means if I add silver nitrate, and you should know that all nitrates are all soluble, and we will review these solubility rules and the keys to understanding them and not just memorizing them. But if I was to add silver nitrate to this solution, we know nitrates are always soluble, so I'd be adding nitrate ions, which would just be spectating, but I would also be adding some nitrate ions. Oops, I got rid of my container, which I didn't want to do. So let's put that back there. And in any case, the silver ions would link up with the chloride ions. So I would make a precipitate, AgCl. In a nutshell, the silver ion and the chloride ion have a larger Coulombic attraction between each other than water for each of those ions. So they ionically bond into a three-dimensional arrangement called a crystal, and they make AgCl solid and a precipitate occurs. Well, guess what? I can take this precipitate out of this solution. I could boil the water, or most of the time we're going to funnel it away, Buchner funnel or filter it away. We separate the water, and then we dry and heat to get all the water out, and I'll have my precipitate AgCl solid dried. We know that we made silver chloride. We would find its mass, okay, and then we would figure out how many moles of silver chloride. And that's easy because we know the formula mass of silver chloride, or we can figure that out. Now, if we have the moles of silver chloride, knowing there's one silver chloride to one silver ion to one chlorine ion, I would get moles of chlorine ions. And if I know the moles of chlorine ions, guess what? I know the moles of the sodium ions. Why? Because in sodium chloride, there's a 1 sodium to 1 chlorine. And that's essentially how precipitation analysis works. There's a fancy word for it, though. It's called gravimetric titration. Gravimetric meaning we're going to use gravity in the case we're going to use mass or weight. I know weight and mass are different, okay, but we're going to use gravity or a scale of mass. And from the mass, okay, we're going to get a how many number. And titration, okay, is a word that you'll hear a lot, is where we use information about one compound to get information about another. So we were using the precipitate, okay, and the information about the precipitate got us information about what we were asking for, okay? So that's how that works. Let's clear this all up. Maybe that is not going to work. I think this one will. Okay, so back to the problem here. So here's some beginning problems with molarity. Okay, I have a student prepares a solution by dissolving 7.96 grams of sodium phosphate in enough water to make a 275 milliliter solution. Calculate the molarities of the major ionic species. This is what's different from last year. Last year we would figure out the molarity of the solution, but most often we don't really care about the molarity of the entire solution. We care about the species in it. Let me explain. Okay, we know that molarity is equal to moles of solute. Okay, in this case it's going to be potassium phosphate. Now potassium is K. We should know it's a group 1 ions, K+. Phosphate is a very, very common polyatomic ion. It's PO3 negative, PO4, so common I didn't get right, PO4 negative 3. And of course, if you want to crisscross, you'll see that you have to have a neutral compound. That's going to be K3PO4. And I don't suggest you memorize any of these polyatomic ions. Just as you go, and as we use these often enough, you'll have most of these by memory. So this is our chemical formula, potassium phosphate. And you notice we're going to be 0.275 liters. Okay, 275 milliliters becomes liters. That's a liter of solution. Okay, tell us that. We added enough water to make that solution. The question is, how many moles do we have? Well, real quickly, we have to convert our grams to moles. Okay, and we know we want to get rid of grams. We want 1 mole up top, and now we have to do a formula mass. We have 3 potassiums, 3 times, and I'm looking on the periodic table, atomic mass is 39.10. Okay, and then we have 1 phosphide atom, and it's 1 times 30.97. And then we have 4 oxygens. 4 times 16. I know that one's 64. I know this one's 30.97. And I know this one is, I don't know this one off the top of my head. I don't know my 39.10 timetables. So 3 times 39.10, and that gives me 117. Where's my 117.3. Let's add all those up. You get a total formula mass. I know you're probably saying, why am I showing you this? I'm not really sure either. Plus 64. Okay, hopefully I get this right. I get a total of 212.27. Of course, that goes there. Let's go find that answer. So 7.96 divided by 212.27, and I get the number of moles to be 0.037. Let's go 4, 9. Another 9 behind there, but good enough. We'll go 0.0375, and that's the number of moles. You'd plug, of course, that value in back into molarity, and what we get is 0.0375 divided by 0.275, and I get a molarity of my potassium phosphate. Oops, a little doohickey again. So I get my molarity to be 0.136. We'll just round off at this point, and that's my molarity. Okay, you can just write this number and get rid of that. That's your molarity. Okay, now that's the molarity of what, though? That's the molarity of K3PO4. That's assuming, party people, that K3PO4 is a particle or a molecule, and we know better. That's an ionic compound. That dissociates into 3 potassiums, and we know it's soluble because all group 1 ions are soluble. And you may say, Mr. Gutsy, how do I know group 1 ions are soluble? Well, these are the biggest atoms, and when they become positive by losing an electron, they get a little bit what? They get a little bit smaller because the protons outnumber the electrons. So these atoms, K, become cations or positive ions, and they get a little smaller, but they are still essentially pretty big ions. And if you're a big positive ion, your charge density is too big to actually attract something negative that's smaller. We talked about this in class. You're stretching out positive 1 over a big area, so only this small area hits something else that's smaller, and you don't feel the entire positive 1. Anyway, getting back on track here. Getting rid of that. Okay, I'm getting, let's do more of that. So I have 3 potassiums, and I have 1 phosphate ion. Probably don't have to say 1. Okay, so what is the molarities of these individual species? Well, if for every 1 K3PO4 there's 3 potassiums, you probably could say, well, the molarity must be 3 times that. And you can write this out. And I like when you write this out gravimetrically. Okay, so you have 0.1 dimensionally, I should say, 0.1364. That's molar of what? K3PO4. And watch what I do here. I'm going to get rid of K3PO4. It goes in the bottom. For every one of these, there's 3 K pluses. And you can see that I'm multiplying it by 3. And what do I get? I get oops, another doohickey. Sorry. Alright, so another doohickey. 0.4. We're just going to leave that 0.409 I'm getting. Okay. And I'm supposed to have at least 3 sig figs, so that looks good to me. Okay, and that's the molar. So the potassium ions are actually 3 times the concentration of this fictitious particle. Remember last year we were finding molarities of salts and doing it this way, but really wasn't the right way because this is not a particle that sticks together anymore. They dissociate into the individual ions. And in real chemistry, you want the molarity of the individual particles. Okay, the phosphate ion's easy, right? Because there's only one phosphate per 1 KPO4, so the molarity of the phosphate ion, okay, so the PO4 -3, its molarity, of course, equals the original. And the K plus equals that. So there are the two, okay? And again, a lot of mess here, looks like, to get something that's not too difficult, but something new to think about. Okay, now the next step is calculate the molarities of the major ionic species present if 42 milliliters of this solution is added to 100 milliliters. Okay, well, molarity is going to be constant no matter what size you take. So we're going to take the molarity and then we're going to dilute it. And there comes my dilution formula. Okay, now I'm going to get rid of some of this stuff up here. So just to keep this even, I want to get rid of all this stuff that we already have. And if you want to look back, you can certainly review the video. Just going to try to keep things interesting, or not so interesting, but just clean. All right, any case, so here's what I'm going to do. Okay, I'm going to take and we'll do phosphate first because that's easy because it's a 1-to-1, and there comes my doohickey. Okay, it's my finger that keeps hitting something. Okay, so I'm going to take my phosphate ion, PO4, -3, okay, and we're just going to look at it. We know that there's one what? Well, one phosphate per the concentration, so the concentrations are the same, and I'm going to use MV equals MV. And the molarity of the phosphate ion is the same as the original, so 0.1364 molar times the volume. We're going to have 42 milliliters of it. Okay, and that's going to be equal to, well, the new concentration. And then we're going to solve for M and the new volume. This is important, you get this part. Okay, we have 42 milliliters of it, and now we're going to add more till we get to the 100 milliliters mark. So if I have 42 milliliters, what's the new concentration of the new volume? I will have a lot of students tell, well, it's 100 minus 42, and that'd be wrong. Okay, the new volume of your solution is 100. You'd have to add the 58, I guess in this case, you have to add 58 milliliters of water to do that, but what goes in here is the new total volume, okay, milliliters. So obviously it's 13 is plugged in my calculator, 0.1364 divided by 42.0, okay, and I get my molarity to be, and it should get smaller, 0.00325 by rounding off. Okay, so 13 times 42. I think I made a mistake here, party people. Hold on. So that looks like 0.1364 times 42. Divide by 100. Yeah, I'm really off. Okay, sorry, may say. Do make mistakes, and I am tall. So here we go. It is 0.05. Oh, Christmas in July. Okay, 0.05 7273. Okay. And the K plus is simple. What was our same idea for the K plus? You're going to do the same thing. There's another way to do this. MB equals MV. Let's do the K plus very simply. I'm going to do the K plus a different way. Okay, I'm going to give myself some space here. Get this out of the way. Get this all out of the way. Here's the way that I'm going to do it. Do it using dimensional analysis. Okay, and I'll just change the inks here. Okay, so what was given to me is that I have a concentration of I have what, 42.0 milliliters, okay, of my K plus solution. Okay, now here's what I'm going to do. I'm going to convert to liters. And for those that are not understanding, I am doing the same thing, but I'm using basically dimensional analysis. I'm using the units and stoichiometry. This is the way that I want you to learn as well. So just pay attention. So we're getting rid of the milliliters. I want to go to liters. I know that for every 1 liter, of course, there's 1,000 milliliters. Mr. Grodsky, why am I going this route for? Because this is the route you want to use for very complex equations or problems. Okay, so now I have liters are gone. I mean, milliliters are gone. And the reason I went to liters is I want to use the molarity as a conversion factor. Look at this. I want to go to moles. And it's not 1 mole equals 1 liter. Okay, for every 1 liter, how many moles do we have? Well, what's the exact molarity? There's 0.409 moles per 1 liter. So I'm using the molarity as a converting factor, and now I got moles of K. All right, now that's great. What am I going to do with that? Okay, well, I want to dilute it. I want to dilute it by a new volume. Okay, well, I have 42 milliliters of it, and now I'm going to have 100 milliliters of it. So I'm going to put this over my new volume, which is 0.100 liters. I'll put a 1 here, and what do I get? Moles over liter. And let's find the number. 42 divided by 1,000 times 0.409, okay, divide by 0.1, and I get 0.1718. Probably should round to 3 significant figures, but I'm not abusing if I'm off by 1 molar. Okay. Now you may say, am I right, Mr. Gradsky? Am I wrong? I don't know, but one way to look at these two answers, isn't there 3 times the number of K pluses in phosphates? So shouldn't the molarity, even when it's diluted, they're both being diluted, shouldn't this be, shouldn't this number, if you times it by 3, equal that? Yeah, it should. Okay, and it's pretty darn close. Okay, so that's how you take care of that. And again, you may not love this method, but this will be your friend. Yes, you can use MV equals MV to your heart's desired, but you gotta learn this method, especially as we get more complex problems. Okay, so number 2 is essentially the same. Number 4, okay, is asking what mass of silver chloride will be recovered if excess sodium chloride solution is added to this milliliters of an aqueous solution. So they're saying how much. Okay, please try that one. Okay, and if you so desire, if you're really ahead of the game here, you can try this one. This is a lot like what we did last week, but we have a little bit of precipitation analysis going on. Okay, so 4 and 5 you're on your own. Okay, and we'll leave that one for another day. All right, rock on.